Okay guys, back with part 4 of our review on work power in simple machines. I'm looking at numbers, starting here at number 7. A machine requires a force of 250 newtons over 75 meters to produce 400 newton force over 25 meters. Remember that simple machines, well, what do? They don't do work for us, they help us to do work. That is, it's going to change either the force that we have to apply to do it or the distance over which we're going to apply that force. If we take a look at this problem, it says a machine requires a force of 250 newtons. Well, 250 newtons, if it requires it, that force that we're talking about is going to be the effort force, FE. That's what has to be put in. Over a distance of 75 meters, that's going to be your DE, your effort distance that you have to put in. If we look down here, it then says a 400 Newton force is what's going to be produced. That is our resistance force. That's what the machine's going to do. Over a distance of 25 meters. That is our DR. That's the resistance distance, how far the machine is going to move it. So we're asked to look at the efficiency of our machine, the AMA, the IMA of this machine. So let's start with efficiency, and there's two ways that you can calculate it. You can either do work out over work in times 100, or you can do the mechanical advantage over the ideal mechanical advantage times 100. In this case, since we're looking at work, it's easy enough to start with our efficiency equation. So let's start filling it in. We need the work out. So to get our efficiency, we need work out, and work out, right? What is the machine doing? That is the resistance force times the resistance distance, right? Force times distance is work. Work in is what you are doing, what you're supplying to the machine. That's the effort. The effort force times the effort distance. Multiply it by 100 to make it a percent. So what were these? We've already identified them. We are going to have a 400 Newton force, and that's going to be going a distance of, what is our distance that we're going to do? 25 meters. And we're going to be doing that for some effort, which is 250 newtons. And the distance there is going to be 75. So we're going to have to calculate the work in, and we're going to have to calculate the work out. We're going to divide that. We're going to multiply by 100. So that's going to come out to be 53.3%. It then asks us to find the actual mechanical advantage and the ideal mechanical advantage. Let me just come back up to our equations. If we're going to find the actual mechanical advantage, or what we just call the mechanical advantage, that's the relationship of the resistance force to the effort force. So if we go back up into the problem, we see that there's 400 newtons for our resistance force. We only have to supply 250 newtons as our effort, which gives us an actual mechanical advantage of 1.6. If we take a look at the ideal mechanical advantage equation, this is the one that works with distances. So let me bring that down. So if we take a look at our effort distance and our resistance distance, notice again that these are flipped, right? In terms of the effort and the resistance. In the problem here, the first part, we have resistance force and effort force on the bottom. Here, effort distance is on the top. The effort distance is 75. The resistance distance is 25. And that's going to give us an ideal mechanical advantage of 3. Typically, your ideal mechanical advantage is going to be bigger than your actual mechanical advantage because there is going to be energy lost. That means there's going to be lost work because of friction inherent in the machine. Let's do one more for this video that deals with pulleys. A 1,500 kilogram load is attached to a single movable pulley. It's helpful if you can draw what that's going to look like. So a single movable pulley is going to be attached to some surface. It's going to be raised by the effort force some distance, dE. The pulley that has the load on it, which is essentially a weight, this is 1,500 kilogram mass, right? That's not the actual load, it's not the resistance, because we have to find the weight of that. And if we're taking a look at this, oh, I'm sorry, I forgot to mention that the pulley system is 50 kilograms. If we're looking at this system, we're saying, I have a movable pulley. What is the mechanical advantage that I'm getting here? Well, ideally, if we're looking at this machine, I'm going to look over here and I'm going to see that this is a lifting rope. And if I'm pulling up on a rope, that's a second lifting rope. So this should have an ideal mechanical advantage of somewhere about 2. Right? If we actually measure the distances that we're going to get something slightly different from this. But let's look at the problem. It says the string is going to be pulled 15 meters with a force of 12,500 newtons. Well, if that's what you are doing, that's what you're putting in, the work that we're putting in is Fe times dE. Well, in that case, that is 12,500 times the distance of 15. That gives us 187,500. If we look at the work that we're getting out of it, well, what is it doing for us? What's it going to be lifting? Well, we want to use the weight, Fg. That's what we're really lifting times the resistance distance. So we can use mg times our distance, which is going to give us our mass, which was 1,500, times 9.8, times the height that we're going to lift this. Well, how far is it going to move? Well, in this case, it says it's going to move 7 meters. That's going to give us 102,900 joules. Okay, so we've got the work in and we've got the work out. I'll be back in the next one with one more dealing with a different type of machine.